primary is a good start. Okay, I just got the recording going. On methyl cyclohexane, the most stable place to put a radical would be the tertiary carbon, just like that would be the most stable place to put a carbocation. On 1-methyl cyclohexene, you decided to put the radical here, and we can describe this as what? Not just a primary radical. Its relationship to the alkene gives it another important name. Primary methyl, again, is like two different carbon substitutions. Primary or methyl. This is primary, but it's primary, not vicinal. Vicinal means two things adjacent to each other. Vinylic means attached to an alkene carbon, and this is not. So it's not a vinylic radical. By the way, vinylic radicals, not as stable. This is a primary, starts with an A. One more time. Not alkyl, allylic. So tertiary radical versus a primary allylic radical. Allylic is the description of a position adjacent to an alkene. Allylic positions are impacted by the alkene. In the case of this allylic radical, there is a resonance form. This is why I brought up MO at the end of last week. When you have an allylic carbocation or an allylic radical, you are describing resonance. You may only be showing one resonance form, but if you can say allylic carbocation, allylic radical, then you are saying there is resonance between that cation or that radical and the alkene. And I want to point out how I observe the relationship. I call these 1,3 allylic resonance forms. The reason I call them 1,3, here's position 1, 2, 3. Here's position 1, 2, 3. And you'll notice that the radical moves between positions 1 and 3. Does it really move? MO theory says that this radical electron, as opposed to the pi electrons, this radical electron sits in a molecular orbital that is only on positions 1 and 3. The orbital does not exist over atom 2. So MO theory says the radical is on positions 1 and 3. How do we show that in Lewis dot structure form, bond line form? We show that as two resonance forms. All right, I'm going to redraw this structure because that's not the only allylic position that you could have chosen. This primary carbon is allylic. What else is allylic? Here? Here? Good. That's an allylic position, which means I could form an allylic radical there. And there is another allylic position. On this position that Elliot didn't want to claim. That is also an allylic, secondary allylic position. What is more stable, a tertiary radical or an allylic radical? Allylic is more stable because the reactivity of that electron is delocalized. It's not any one carbon that hosts the radical. which makes it less reactive. What is more stable, a primary allylic radical or a secondary allylic radical? Why? No. Because radicals trend with carbocation stability. More substituted, more stable. More substituted radical, less substituted radical, more stable. All right, let's identify the 1, 2, and 3 positions here. I'm just going between the alkene and the radical. It really doesn't matter which positions I call what. So here's 1, 2, and 3. Here's 1, 2, and 3. I would like you guys to show me the other resonance form for these two allylic radicals. If it helps, let me first add the electron arrow pushing to this first form that shows you how to form the second form. You don't necessarily need it. You could just match the patterns of what you did here to these new structures. But here's what the arrow pushing looks like. Radicals move by half electron arrows, fishhook arrows we call them. So here's a fishhook from the radical to the pi bond, which means the pi bond now needs to split into two radicals. So one of the pi electrons completes the pi bond here. The other pi electron goes to carbon 1 and becomes this radical. Either map the pattern or use the arrow pushing, draw me the other resonance form for these two allylic radicals. Map your carbons. Pay attention to how the bonds move between those mapped carbons. If the radical is on position 3, now draw it on position 1. If the radical is on position 1, now draw it on position 3. One electron, one hook. So like you've got 2 heads on an arrow. I want to see 1. So just erase half of it. And then remember, electrons are never tossed away by an atom, but they can be used. So this electron comes here. Oh, you have 2 heads there. Oh, what kind of 2 heads can I show you? It looks weird, right? There you go. And it's the same thing here. 1 arrow, 1 arrow, 1 arrow. Yep. And then there's actually, that's just describing one of the 2 pi electrons. There's another arrow that goes over to carbon 1. You want to put it in a new position. These are not arrows. These are resonance arrows. So they need to have, they need to be double-headed. It points this way and this way. No, those Nope. These ones actually. So in green, I don't want to see. Oops. I don't want to see an arrow. I want to see what they call a fish hook. This is 2 to 2. This is 1. So there, show me the fish hook instead of arrows. Here, resonance is represented by a double-headed arrow. So you were right. The double-headed means another arrow on the other side. When you relate resonance forms,
Yes, you're trying to make
2 arrows.
You're shifting the double bond.
D, do you need a sheet?
Yeah. Yeah. So the double bond shifts to the left.
So here's positions 1, 2, and 3. How did you get pi bond and radical to carbon 4 that's not in positions 1, 2, and 3? Yeah. If this is position 1, now draw the radical on 3. And the pi bond will be between 1 and 2. Like this. We'll go through it. You did. Great job. Yeah. This one actually looks just like a mirror image. But carbon, that metal carbon on top, it has CH3. It should end with C. Okay, sorry. Yeah. Carbocations are actually not stable on the reactions either. I'll talk about it. Okay. We didn't talk about it actually, so let's go through it. Okay. Yeah. I can explain it. But it's not. We want radical and alkene to be positions 1, 2, and 3. So now it's actually just gonna look like this. All right. Let's go through these. Here's how I want you to use the mapping. Identify positions 1, 2, and 3. 1, 2, and 3 doesn't matter what is where, but it should be the radical and the alkene carbons, the allylic position and the alkene carbons. This goes for carbocations as well. Allylic position and alkene carbons. Now, if you drew your radical on 3, now your radical will be on 1. If your pi bond was between 1 and 2, now your pi bond is between 2 and 3. This is the most stable radical in this whole structure. Why? It's both tertiary and allylic. Primary allylic is more stable than tertiary alone. So remember, we said increasing substitution increases stability, kind of shields that reactive spot with more electron density. But resonance has an even better effect, so that low substitution with resonance is even more stable than high substitution with no resonance. Here's positions 1, 2, and 3. Radical is on position 1, so now it's on position 3. Pi bond between 2 and 3, so now it's between 1 and 2. These structures are identical. There's no difference between them. That's great. So we had 3 allylic positions, and from that, we actually got a total of 1, 2, 3, 4, 5 different carbon radicals. So if this starting material were to form a radical, this would be the least likely to form, because primary forms less stable than secondary. This would form equal to this, which means I'd have a possibility of 3 different carbon radicals in this reaction. Here's 1, here's 2, here's 3. If I were predicting a product, if this radical were to react with something and form a product, there are 3 different structural products. One where the radical is at each of these unique positions. Okay, I wanted to point out something about instability. For carbocations and carbon radicals. If you ever place a carbon radical or a carbocation onto an sp2 hybridized carbon, there is no resonance because that positive charge or that radical, it's in an sp2 hybridized orbital, so it cannot be delocalized. It can't be moved around. So this is very unstable. This does not like to form. Similarly, to put a positive charge onto, or a radical onto a sp hybridized carbon, not very stable. No resonance to stabilize it. And I want to draw your attention to pKa values. When we look at sp3, sp2, and sp hybridized carbanions, what we're looking at here versus here versus here, we're just looking at different substitutions of carbons with the same amount of electrons. What I'm telling you is that sp, okay, this is bad. The more alkyl type carbon, more stable with less electrons. The more alkene type carbon, less stable. The more alkyne type carbon, the least stable with the least amount of electrons. When you flip this trend on its head, you get more stable with more electrons at the sp position. Do you remember that we said in karyo, orbital determines acidity? More S character, more acidic, more stable conjugate base, less reactive conjugate base. And we said the sp carbon is the most acidic CH bond, which means it's the most stable carbanion. This has a pKa around 25. Whereas the sp3 carbon has a pKa in the 50s to 60s. That is 10 to the 25 times more basic. 10 to the 25 times less stable. 10 to the 25 times more reactive. Consider a spectrum. Carbon with 2 electrons, carbon with 1 electron, carbon with 0 electrons. Okay, 0 lone pairs, 0 non-bonded electrons. 0 with 2 non-bonded electrons, 1 non-bonded electron, 0 non-bonded electrons. Our stability goes less electrons on more alkyl type carbons, more electrons on more alkyne type carbons. I have an issue saying sp3, sp2, and sp because technically this is not sp2. It only has 2 electron regions. 2 electron regions, sp. This should actually be drawn linear, right? And this is technically sp, but it doesn't even have 2 electron regions. It only has 1 electron region. Okay, so can you see why I'm saying more alkane type, more alkene type, more alkyne type? Alkyne holds negative charge, alkane holds positive charge. That's the trend. I'm sorry, I've never put this on the board before, so I fear that it looks a little bit messy, but let's try saying this another way. Alkane, alkene, alkyne. This holds a lone pair, and this holds a positive charge and radical. The best. I know. It does feel like the alkene should hold the radical the best. Doesn't that just feel like the middle ground? But it doesn't. Okay. Does that not look like a trend? Do you see the trend? More hybridized, less electrons. Less hybridized, more electrons. All right. Why did I have you talk about radicals right now? Look at how this top part was all about alkynes. And then what are we looking at down here? Any alkynes? No alkynes. I'm having you talk about this because we're going into reactions with alkynes. Sorry, we're going into reactions with radicals. There will be an alkyne precursor that goes into a radical alkene intermediate, but we'll also be doing a lot more with radicals. And actually, this trend reminds me of one of the reactions that we'll be doing, which involves deprotonating an alkyne, getting this, an alkyne carbanion. Why are we able to take an alkyne and deprotonate it? Because it's the most acidic CH bond out of our hydrocarbons here. This is the best acid compared to any of these other functional groups. All right? Okay, well, now that we did that, let's flip to the back side. We're going to dive into reactions. You will notice that my diagram is split. Can you tell me the names of the alkynes that you see? Okay. On the left-hand side, oh, I'm sorry, that's mine, not yours. What do you want to call it? Say Bob. I'm telling my dad you said that.
Oh, Bob.
Okay, not external.
Well, I
Internal. Terminal. Yeah, it's like it ends the carbon chain. Okay, well, let's do IUPAC names. On the left, the terminal carbon here, or the terminal alkyne, 1-butyne, 2-butyne. Great. Once again, these are examples, not full stop everything that can be done. What I wanted to show you, though, is that some reactions are regiospecific, and so I'm giving you a terminal alkyne so that we can highlight the regiospecificity. That's a really hard word. Other reactions are actually stereospecific, and so I'm giving you an internal alkyne so that we can see the stereospecificity. So terminal is here to show us regio differences because internal doesn't have regio difference. And internal is here to show us stereo difference because the terminal doesn't usually create stereocenters, chirocarbons, or stereoalkenes for that matter. All right, let's dive into it. We'll start the same way that we did in our alkene reactions. Going up from the terminal alkyne, let's look at HX addition, specifically when we hold the equivalences, 1 mole of alkyne to 1 mole of HX. We call that one equivalence. Once again, HX, this is a terrible board. HX is regiospecific. Can you tell me the regiochemistry that HX addition follows? Named after an old dead guy? Yvonne, you got it? Markovnikov. When we do one equivalence here, that means that I only add across one of the 2 pi bonds. I end up with a vinylic alkene. H adds to the terminal carbon, X adds to the more substituted carbon. H to the carbon with more H, X to the carbon with less H. What if I add 2 equivalences? Another way of saying 2 equivalents is to say excess. I'll run this reaction with an excess of HX. I must have missed this day in OChem 1. My professor would put X, S, the 2 letters. And I had no idea why on the homework she was telling us this reaction is extra small. I like to just spell it out. I think it's more clear. This intermediate forms, and it behaves just like an alkene when it reacts with the second equivalence of HX. It also adds Markovnikov, which means that we end up with a geminal dihalide. I want that to sink in. The hydrogens add to the same 2 positions, no matter what. This actually goes even if we're on the right-hand side, even if we have an internal alkyne. Say that another way. Even if our alkyne has no regio difference, correct? Both carbons are equally substituted. The 2 halogens will always add to the same carbon. You will always get a geminal dihalide from this addition reaction. Let's move to the right-hand side, and let's show what happens when you react halogenation. X2, 1 equivalence. Do you remember the stereochemistry of halogenation? Anti-addition. How does anti-addition look across an alkyne? When an alkyne has one of its pi bonds consumed, it becomes an alkene. When the alkene is anti, it means that the halogens are anti. We have a trans-alkene product that forms. if we run X2 halogenation in an excess amount of halogen, it first forms this trans divinylic halide, and then that reacts just like an alkene, and it adds a second equivalence of halogen. This would be best described as a vicinal tetrahalide. And you might be asking yourself, why would you need to make a tetrahalide? I don't know. Why do you want to make a tetrahalide? But you can. How do you think the mechanisms for these reactions compare to the mechanisms that we already learned? Similar? Different? The only difference is the substitution of the carbons and the number of times that you can show it happening. So we'll get a chance to dive into these reaction mechanisms a little bit later. All right, I'm actually going to move back to the left-hand side. We're going to skip over the haloether, halohydrin. Those are not as common in these reactions. What we're going to look at are hydration mechanisms. Do you remember how many ways we could hydrate an alkene? 3. Acid catalyzed hydration. Markovnikov with a carbocation. Oxymercuration reduction. Markovnikov without a carbocation. And the last one? Hydroboration, oxidation, anti-Markovnikov. We're narrowing it down to 2. We're combining the 2 Markovnikov products. Oxymercuration no longer has a 1,2. This is no longer oxymercuration reduction. Also notice we're not using mercury acetate, we're using mercury sulfate. Sorry, one other reagent that goes with this, H2SO4. This is essentially a combination of acid catalyzed hydration with oxymercuration. Although we still just call it oxymercuration. The product that we make is a ketone. What? Come on, were you expecting that? If you did your reading, you might have expected that. Does it look like a hydration product? When we hydrated alkenes, we said put an H on one carbon, put an OH on the other, added water. Have I added water to this compound? Have I added H2 and O? Does there need to be an OH? Right, water is H2O. So as long as I add the equivalence of 2 hydrogens and 1 O, that's adding the chemical formula of water. That's hydration. I know an OH makes it feel more like hydration, but OH is not water. OH is alcohol. So adding H and OH was adding an equivalence of H2O. Have I added an equivalence of H2O? Yeah. I go from CH to CH3, that's 2 H's. And I go from 0 oxygens to 1 oxygen, that's O. I've added an equivalence of H2O, but it actually looks more like 2H and O. Here's a good way to map the carbons so that you can see this change. Did the hydrogens add to the carbon with more hydrogens? Yeah. Carbon 1 has more hydrogens than carbon 2, and the hydrogens added to that carbon. Okay, this is not something that I'm going to ask you to be able to repeat, although it is really good insight. That is not the product that forms initially. That actually forms by an acid-catalyzed structural rearrangement called tautomerization. I'm giving this to you as a teaser because my OChem 2 class right now, they're going into tautomerization reactions. What originally forms on that structure is we do form an H and OH, and it adds Markovnikov. And then an acid-catalyzed structural rearrangement occurs. I should be a lot more careful with my arrows. This does not happen all in the same step. Man, I shouldn't even show that to you guys. It's so risky. I don't want you to think that's what's happening with the arrows. I'm just going to circle some things. A double bond will form here, and the hydrogen will move over here. This is done by a catalytic process. If you're interested in seeing it, you can watch my lecture recording from tomorrow night for my OChem 2 class. I'm not going to ask you to need to show me it. I just want you to recognize if what helps you predict the product is first snapping on H and OH, Markovnikov, then you can predict where the CO double bond will form. The CO double bond forms at the more substituted carbon, where the OH originally adds. So what functional group would I get here if I ran hydroboration oxidation? First, BH3, second, basic aqueous basic aqueous potassium hydroxide. What? Hydrogen peroxide. Basic aqueous hydrogen peroxide. Same as our hydroboration oxidation of the alkenes. What functional group do you predict? Ketone? What was the regiochemistry of hydroboration oxidation? Regiochemistry. This was an anti-Markovnikov reaction. If the Markovnikov reaction formed the double bond on the more substituted carbon, the anti-Markovnikov will form the CO double bond on the less substituted carbon. Can you predict that product? Let's draw a carbon chain, first of all, a 4-carbon chain, and let's map our carbons. Here's carbon 1, 2, 3, and 4. Anti-Markovnikov means my hydrogens won't add to carbon 1, the less substituted. They'll add to carbon 2, the more substituted, which means the oxygen adds to carbon 1. And so my CO double bond is on carbon 1. And that functional group is what? Aldehyde. Very good. I hope you have continued to study your functional groups because they do not go away. Asterisks. when possible. There's no reason you can't take an internal alkyne and run hydroboration oxidation. The problem is there is no carbon more substituted or less substituted. Either carbon that gets the two hydrogens and the other, the CO double bond, is a ketone. Doesn't matter what reaction you run. When there is no room for regio differences, then it's only a ketone, regardless of which reaction you give. Does that seem fair? More than one way to get there. Do you think that this also goes through the same intermediate? Well, not the same intermediate, but the analogous intermediate. Here, the OH and the H simply switch positions. Now the CO double bond will form on the less substituted carbon, and then this hydrogen moves to the more substituted carbon. Am I ruining it by drawing in these lines? I fear I may be. Is this tautomerization base catalyzed or acid catalyzed? We said that oxymercuration was acid catalyzed into the ketone. Can this also be acid catalyzed into the aldehyde? There's no acid, right? This is actually base catalyzed into the aldehyde. They use different catalysts, but there is a breaking and forming of bonds in order to do this. If you were to name this functional group, the one that we see here, what would you name it? An alcohol attached to an alkene is called an enol. Makes sense. All right, let's keep going. Let's move back to the right-hand side. I want to take this internal alkyne, and I want to show you 3 different ways that we can hydrogenate. Remind me what hydrogenation is. Adding 2 hydrogens. That is H2PDC. How did that go this week? Those of you that have done it. Yeah? Did it look like palladium or did it look like carbon? Huh? It looked like charcoal, right? It was just black. That's just carbon. The palladium is in there somewhere. And the hydrogen gas, cool to make or not cool to make? A little cool, right? A little back to Gen Chem 1 chemistry, redox reactions, HCl and zinc to push out some H2 gas. Pretty fun. That's if you're doing it in a setting like ours. If you're in a research lab, you probably have a tank of hydrogen. And you would, quite literally, just fill up a balloon with that hydrogen gas, and then you just put that balloon over your apparatus. And you would just allow all of that excess H2 to come in. Intentionally saying there, excess. I'm not writing excess H2, but there is no way that you run this reaction where H2 is not the excess reagent. It's always an excess. To be clear, this says 2 pi bonds, 1 equivalence of H2. You are assuming excess. enough H2 to satisfy all of the pi bonds in the structure, whether it be just one alkyne, 3 alkynes, 2 alkenes and an alkyne. You assume always enough H2 for everything to be reduced. What's the product we get? What is that functional group? Alkane. Plain and simple. Same thing happened with alkenes. Alkene hydrogenated to alkane. Alkyne hydrogenated to alkane. Some places will refer to this reaction as reductive hydrogenation, as if there is another type of hydrogenation. Pretty much every time you add hydrogen to a carbon chain, you are reducing those carbons. They now get to take electrons from the hydrogens. That's gaining electrons, that's reduction. I find it so silly that they call it reductive hydrogenation. Duh. I like to call this full hydrogenation because the next two reactions are not full hydrogenation. They are partial hydrogenations, and they come with slightly different reagents. The first one is when we use Lindlar's catalyst. We'll write this as H2 and Lindlar's cat. If you are curious what Lindlar's catalyst is, don't be. It's a mixture of things. It involves the palladium, it involves carbon, it involves an organic molecule called quinoline, and it involves barium carbonate, I believe. Lindlar's catalyst sounds like it is catalyzing a reaction to occur, but Lindlar's catalyst actually poisons the reaction. Lindlar's catalyst allows the alkyne to react with H2. Do you remember the stereochemistry of hydrogenation with alkenes? Was this syn, anti, or random? One more time. This was a syn addition reaction. It will still be syn addition. If the anti-addition halogenation gave us a trans alkene, syn addition hydrogenation gives us a cis alkene. Lindlar's catalyst allows the alkyne to react with H2, and it poisons the reactivity of the alkene. This alkene forms, and the alkene is inhibited from being hydrogenated. Just for full context, this alkyne is first reduced to this alkene in our normal conditions, and then this alkene, as alkenes do, reacts in these conditions to become an alkane. This is an intermediate in the production of the alkane. Lindlar's catalyst stops this from reacting so that it can be harvested. Now you can create a cis alkene from a linear alkyne. What if I don't want a cis alkene? What if I would like a trans alkene? Fine. Partial hydrogenation with metal in ammonia. The metal that we're using is either sodium or lithium. These are 1 electron elements. Notice that is not sodium ion. It's not lithium ion. That is elemental sodium, elemental lithium. Dangerous stuff, right? Because if you expose this to the water in the air, they'll explode. They're incredibly reactive. Here's how we write it over the arrow. Na, comma, NH3, or Li, comma, NH3. Some places will tell you that the ammonia is liquid. So they'll say Na, comma, NH3 liquid. I typically have introduced this chemical at this point in the semester, but I haven't yet, so I want to make this clear. You'll see this over the reaction arrow as Na, comma, NH3, which is not the same as this chemical, Na, NH2. Do you guys remember seeing NaNH2? Have we looked at it early on when we did acid-base chemistry? Maybe. Its name is really stupid. Its name is sodium amide. Why is that a bad name for it? There's no amide present, right?
Yeah.
The amide is the CO double bond connected to a nitrogen group. That's not a CO double bond connected to a nitrogen group. But remember, nomenclature, IDE indicates an anion. This is NH2 minus, which is like an amine, but now an anion. So give it the suffix IDE and you get amide. Sodium amide is Na plus NH2 minus, which is not the same at all as elemental sodium and liquid ammonia. Both neutral reactants, ionic compound. You guys seen those memes that say like, sodium will explode and kill you. Chlorine, toxic, kills you. Sodium chloride, delicious on food. That's what's going on here. Crazy reactive, a base. Partial hydrogenator, a base. Very different chemicals. Okay. And what do we get? A transalkene. This reaction has a radical intermediate. This reaction actually has 2 radical intermediates. And it is the nature of the radical intermediates that defines the transalkene structure. First, the sodium acts as a reducing agent, and it gives an electron to the alkyne. Giving an electron to the alkyne means you'll have to break one of the pi bonds into a lone pair. There are 2 configurations that can happen. Either a transalkene is formed and the radical and lone pair are anti to each other, or a cisalkene forms and the radical and the lone pair are cis to each other. We already know which of the alkene forms. Can you argue why that alkene forms based on the nature of the radical and the lone pair? This goes back to Gen Chem 1 knowledge. I know for a fact I gave 3 of you this information one day in class, so I'm sure it's super well understood in your minds. The same reason we prefer one of these alkenes over the other is the same reason tetrahedral water does not have bond angles of 109.5, but has bond angles of 105. I love electrons, they're so cool. Non-bonded electrons repel each other more than bonding pairs of electrons. In water, the two lone pairs on oxygen repel each other greatly, the bonding pairs less greatly, and the bonding pairs repel each other the least. So the lone pairs take up most of the space on the oxygen, cramming the bonding pairs closer to each other. This would experience the greatest electron repulsion because the non-bonding electrons are close to each other, and so the structure avoids forming this. Here, the non-bonding electrons have no repulsion. They're exactly across from each other, so they don't impact each other's place in the molecule. The reason metal in ammonia creates a transalkene is because of VSEPR theory. Valence shell electron pair repulsion. Next, the ammonia plays a role. Ammonia here is an acid. It gives away one of its hydrogens to the lone pair on the carbon. And then the same thing happens. Sodium gives another electron, turns the radical into a lone pair, and then that lone pair reacts with ammonia and creates the transalkene. Can you tell me what byproducts are generated through this reaction? It's two equivalences of the same byproduct. Why don't you turn into your groups, discuss for 2 minutes, and then I'll give you a break. What byproducts form? Now, two equivalences of one byproduct. Should I draw the hydrogen? Tell me, what do you think becomes of this NA? Oh, NA is a rapid. Only has one valence electron. Oh, yeah. Okay, so yeah. What happens to NH2 after it takes over? Together, that makes yeah, which is on the board, right? It's actually a different reagent that we use for certain things, and stack on this stuff. Terrible.
Well, no, it's not.
It's on the board. Yep.
You need sodium twice because sodium is much important.
It gives us a sodium is right. It's carbon. Notice how it made the carbon have a negative charge? What's valence of that negative charge? Positive charge. Where? Sodium gives a less charge. All right, take a 5-minute break and I'll tell you the answer when we're back.
Sodium really wants to get rid of its own base. I guess this is I'm going for This seems strange. You would have to be able to bond 3 sodiums. Yeah, because we're given, I don't know if we're seeing so how many are we working with just these 6 hydrogens and 2 negatives?
Yeah, right, because
I was just going, I'm pretty sure it's like 2, because you need more balance and you need.
use like a larger tube, it's like a vacuum. It will do it so fast, and it will be so people. Yeah,
Aren't the H's being put into the
Most of course.
Yeah, that's a good question. If it isn't, then That's actually, I didn't see the very Oh, it could be N,
Yeah.
H2.
Thank you.
Two N, NaH2. Two molecules of whatever that would make a lot more sense. Because then we're getting the exact ones. Those are my two guesses.
I just signed up for it. Well, I don't know. I might drop the class because they're Of course I am. It's not, like,
They're merging. No, they're merging each other.
it's not a value, but
Okay.
oh, yes. It's like on Mondays. Oh, maybe it's the same class then. Yeah, okay.
Did you guys figure it out? What we're missing? No? I did, my red marker. What happens to Na? It gave its electron here. Do you know how many electrons Na has? How many valence electrons? 1. So sodium is actually a radical. After it gives its radical electron, what does it become? This is where I want my red. Do you guys see my red marker? What? Oh no. Do you have my red marker? Oh, Killian has my red marker. I cannot trust him. He's gonna get down to the lab, realize what he has, and he's never gonna return it. Okay. All right. Let's pull it back together. Sodium has 1 valence electron. That makes sodium a radical. It's also a very good reducing agent. It gives it away because it likes to become what ion? Na+. What is balancing this newly formed negative charge? How do you balance a negative charge? You need a positive charge. Where is the positive charge? It's on sodium. Sodium gives away its electron. It becomes sodium ion. Then ammonia gives away a hydrogen. It's acting as a base. What is the conjugate? I'm sorry. Ammonia gives away its hydrogen. It's acting as an acid. What is the conjugate base of ammonia? NH2 minus. Which means at this point, I have created an equivalence of sodium amide. Okay, remember, we're not reacting with sodium amide. In this case, we're actually producing sodium amide. And later, we are going to use sodium amide as a reactant, as a base. So I want you to pay attention to how weird it is that we're using sodium and ammonia. We produce sodium amide as a byproduct. Then again, sodium radical gives away an electron, becomes sodium ion. Ammonia gives away a hydrogen, becomes amide, which gives me a second equivalence of sodium amide byproduct. There he is. Thank you, Killian. I appreciate it. Well, I was going to do that in red, but it doesn't matter, does it? Okay. We've got one reaction left on this diagram, And then the other reactions we're going to look at are down here. What is the only other reaction that we saw? Not the only other. What other reactions did we see in alkenes that we haven't looked at yet with alkynes? We skipped haloether, halohydrin. What else have we not seen yet? Hydrohalogenation, HX addition. Yep, we got it. Diol addition, we're going to skip. Oxidative cleavage, we're going to do. What's the only other one? Epoxidation. We're not going to see epoxidation. So our last reaction up here is oxidative cleavage. And this time, there are not two options. There's just one. This is O3 and H2O2, or hot potassium permanganate. That's reaction number 8, oxidative cleavage. That means that in this case, it really is truly just oxidative. There's no reductive ozonolysis for alkynes. There is one functional group that we form from alkynes. We form only carboxylic acids. You remember with alkenes, reductive ozonolysis could give us 2 aldehydes, 1 aldehyde, 1 ketone, 2 ketones. Oxidative ozonolysis could give us 2 carboxylic acids, 1 carboxylic acid, 1 ketone, 2 ketones. Only carboxylic acids here. Because the carbons of the alkyne are only bonded to 2 carbons, and we're cleaving one of those 2 bonds. So it's only going to be bonded to one other group. No possibility for ketones. So positions 1 and 2 will get cleaved. That means I get a structure here like this. That's carbons 2, 3, and 4. Carbon 1 also becomes a carboxylic acid, but because carbon 1 also has a hydrogen, carbon 1 gets oxidized into a dicarboxylic acid, and this dicarboxylic acid is not very stable. Did we talk about this? I think we did. What's the name of that compound? Didn't we talk about this? It's in your blood, it's in your soda, it's becoming more and more in the oceans. It's the reason. Microplastics are organic, but so you're not far off, but no. This is carbonic acid, and carbonic acid readily decomposes into CO2 and H2O. So if you do oxidative cleavage of an internal alkyne, well, great. Then you can get 2 carboxylic acids. If you do oxidative cleavage of a terminal alkyne, you'll always lose one of those carbons to carbon dioxide. What questions do you guys have on these first 8 reactions?
So wait, that happens.
Pretty much immediately.
So that only happens if you're doing it on a terminal, is that what you're saying?
An internal carbon, an internal alkyne would not have the capacity to form carbonic acid.
Okay.
We're saying that this hydrogen gets converted into an OH group, and when the bond cleaves, it creates an OH group. If you cleave this, you'd get 1 carboxylic acid, another carboxylic acid. Yeah? Okay, I want to pull up our learning objectives document. I want to make sure that I am on the right track with our reactions. Other questions that you guys have on these reactions so far? Easy peasy lemon squeezy? No? Hard lemon hard? Good. All right. We're going to move on to the next chart then. I'll leave this up for a little while. I'm going to make some space over here if that's okay. And we're looking at 6 new reactions down here. And we're starting with just this terminal alkyne. The first one I want to introduce is actually an anti-Markovnikov HX addition reaction. The reason this is getting brought up now is because now we have some knowledge about radicals. And we're talking about radicals again. And the anti-Markovnikov HX addition is a radical reaction. So let's call this reaction number 9, anti-Markovnikov HX addition. We'll use HX, 1 equivalent, with peroxide. That is the only distinguishing feature. Peroxide. What's the most common example of a peroxide? Hydrogen peroxide, H2O2. If we add 1 equivalence, then we add just one H, just one X, but we swap the regiochemistry. Anti-Markovnikov addition. If we have 2 equivalences, HX, in excess, with ROOR, gem dihalide. Same thing as before. Can you remind me why HX addition was Markovnikov? And don't give me Markovnikov's bullcrap answer. Tell me the mechanistic reason why HX addition added Markovnikov. What charge needed to be stabilized? For our first HX. Stabilize the carbocation by putting it where? On the most substituted carbon. The hydrogen adds first, leaving a carbocation on the more substituted carbon. That's why hydrogen adds to the carbon with more hydrogen, so that the carbocation forms on the more substituted carbon, on the more stable carbon. If this is a radical reaction, then what can we say about the intermediate here? What do we need to stabilize? Also a reminder, if your rule has to have an anti-your rule just to explain reactions, it's not a rule. It's not even a good observation. You didn't look at enough reactions. Sorry, okay. This is a radical reaction, so we're not stabilizing a carbocation. Now we're stabilizing what? Let me demonstrate this actually a little bit better. Previously, with this HX addition reaction, we create this carbocation. Does that look like I drew it weird? It should. That's an sp hybridized carbocation. It's still linear. There's only 2 electron regions, so it's not a zigzag yet. Then the halide adds on. If you want to see arrow pushing, this is as simple as what we've seen before. Pi bond acts as a base. Halide acts as a nucleophile. 2 steps. And then do it again for the second equivalence. Now, I'm not creating a carbocation intermediate. I'm creating a carbon radical intermediate. And carbon radical intermediates, unless they're vanillic, they actually are zigzag. So we actually add the bromine first plus a radical. That means that the reagent here is bromine radical. Bromine radical reacts with alkyne, creates carbon radical plus bromine. Where did the carbon radical form? On the most stable position. Then another equivalence of HBr actually comes in here and provides the hydrogen for the bond, which leaves a byproduct of bromine radical. And that bromine radical feeds in to react with another alkyne, which reacts with more HBr to produce more bromine radical, which reacts with another alkyne, which reacts with more HBr. It's a cyclic process, producing bromine radicals, producing carbon radicals, propagating the radical from one species to another. One question this doesn't answer is, how did the bromine radical come to be? That's where the peroxides play a role. Peroxides are dangerous. Peroxides often form when ethers sit exposed to oxygen. They will form peroxides. And when boiling ethers with potential peroxides inside of it, there's the potential for combustion. Big boom. So we use this peroxide to react with the HBr and produce bromine radical to initiate this whole thing. That's why you want to be careful using peroxide.
I just wanted to say, so I've been using hydrogen peroxide in the lab a lot to remove pigment from zebrafish. Apparently that's something you can do if you mix it with formaldehyde. And I left it in too long once, and their entire organs dissolved. They were dead already.
What do you guys use hydrogen peroxide for? Cold sores? Teeth whitening. Interesting. I didn't know that. Never heard that one. Anything else? Cleaning wounds. Disinfectant. I've seen that. One time on the train in Minneapolis, I saw a guy pouring a bottle of hydrogen peroxide onto an open wound on his leg. It was bubbling, yes.
Okay, so for the radical stabilization, I wrote down earlier that it likes the allylic position.
Okay, correct. But there's no allylic here.
Wouldn't the one carbon left of the double bond?
Well, this is kind of like saying when we dunked the alkyne into ammonia with sodium, why didn't this form an allylic radical? This is not forming an allylic radical because it's a reaction with an alkyne. we're going to come back to actually say there's more radical reactions that we're going to look at. This is not one of them.
Okay. So in this intermediate, you just follow the like most substituted.
Correct. Put the radical on the more substituted carbon.
Okay.
And then when you take this and you react it with that second equivalence of HX, then you place the radical again on the more substituted position, which adds the bromine again to the less substituted position. Listen, none of these mechanisms are going to be on your final exam unless you want them to be. So I'm giving you guys snippets of the mechanism without nailing you down with all the nitty-gritties. Part of that is students in the past say the mechanisms really help them understand what they're looking at. But the arrow pushing and all of that gets a little complicated. So I can dive into it more if we need to, but you have a good point. Why didn't it go allylic? That's because this is actually the radical and the alkyne. The formation of allylics we're going to get to later. Yeah, it's a good point. And it's actually different reagents that help us get there too. All right, other questions? I was trying to be very thoughtful about how I made these diagrams, and I'm worried that I forgot my thoughts because I have a lot of space left and not as many reactions as I thought I was going to have. I think what I wasn't thoughtful about was I was going to show these separately. So we're going to have a lot of extra space here. Sorry. This morning in my Gen Chem class, I was teaching enthalpies, and I didn't have an enthalpy value ready for the reaction I put up, so I said enthalpy equals, sorry, because I didn't want to make up a value. All right, let's look at the last reaction here, which is alkylation of terminal alkynes. That is reaction number 10. If hydrogenation is adding hydrogen, halogenation is adding halogens, hydrohalogenation is adding hydrogen and halogens, hydration is adding water, alkylation is adding alkyl. And what is alkyl? R, right? Carbon chain. Alkyl halide. This is the process of adding a carbon-carbon bond. To this point, we have not created a carbon-carbon bond. We have created bonds between carbons and all sorts of other elements. We have cleaved carbon-carbon bonds, but we have not created a carbon-carbon bond, and that is the framework of organic chemistry, is having carbon chains. So this is an incredibly useful reaction. So I guess since I have so much space, I'm going to go down. The first thing that we need to do in alkylation is we need to deprotonate the alkyne. We will use either sodium hydride, NaH, which is H minus, or we'll use sodium amide, NaNH2. This is a strong base. And what this does is it takes the hydrogen off of the alkyne. That leaves you with a byproduct like H2 or ammonia. And of course, yeah, the negative charge is balanced by a sodium ion. Who cares? The sodium ion doesn't play a role. We're more interested in the nucleophile, the carbon who is willing to share its electrons. What we need then is an electrophile. So, first, strong base. Second, electrophile. I'm going to put that generically as E+, but I'm going to give us a specific example here. Methyl iodide. Methyl iodide, methyl bromide, methyl chloride, they're all electrophiles. They willingly accept electrons by substituting one of the halogens, or the halogen. So what we get here, and this is how I like to predict it. I count towards the carbon that becomes a nucleophile. And then I number the carbon that acts as an electrophile. This is the carbon-carbon bond that I'm going to make. From nucleophile to electrophile, I'm going to create a longer carbon chain. So I like to count through that carbon chain. My new product should have 5 carbons. And I should go from having carbon 3 and 4 to having 4 bonded to 5. Now in this case, carbon 5 was just methyl, but I could have created any carbon chain that I wanted to substitute it here. The electrophile should not be more substituted than a secondary carbon. Even a secondary carbon doesn't work super well. Primary and methyl are the best. This is actually a methyl carbon, not primary. Primary carbons work just as well. Secondary carbons, not super well. Those are the electrophiles that we want to use. I added a 1 carbon chain. I could have added a 15 carbon chain. You do something like this to your DNA, you're technically adding like a 17 million carbon chain, right? Here's the fun thing about alkylation. You don't need to already have an alkyl group on one side. You can start with acetylene, HCCH, and you can alkylate both sides. So if you guys are good, I'm going to erase that diagram on the right, and I want to deviate from this diagram and show you a dialkylation. This method also allows us to create symmetric alkynes or asymmetric alkynes. And we can summarize all of the steps needed over one reaction arrow, rather than needing to show all of the individual steps. Let's take acetylene. And let's react it first with sodium hydride, second with 1-bromoethane. After I've added 1 alkyl group, I'll deprotonate my alkyne again, and then add a new alkyl group. This time, I want it to be benzyl chloride, or chloromethylbenzene. Remember what these numbers are saying? It says that when you head downstairs to lab, you're not dumping all of this together in one pot and boiling it. You're going to get your round bottom flask, you're going to add the first 2 things, mix them until they're done, then add in the second thing, mix them until they're done, then add in the third thing. There's a few different ways that you can try and predict this too. You can look at the product of the first alkylation and then try to map on the second alkylation. Or you can try to number your carbons a little bit differently. Here's what I'm going to do. I'm going to call this carbon 1 and this carbon 1 prime. In the direction of carbon 1, I'll add carbons 2, 3. In the direction of 1 prime, I'll add carbons 2 prime, 3 prime, where 3 prime is just the benzene ring. Remember that this is mapping. It helps me not lose any of my carbons when I start drawing my next structure. I'm going to start by drawing the alkyne, carbon 1 and 1 prime. 1 prime connects to 2, 2 connects to 3. 1 prime connects to 2 prime, 2 prime connects to 3 prime. 1 to 2 to 3, 1 prime to 2 prime to 3 prime. You guys understand what I'm saying when I mean prime? It's that little dash. Just differentiates these groups. Is my alkyne symmetric or asymmetric? Asymmetric. I've got 2 different carbon chains on both sides of my alkyne. Let's take this one step further. Now that I've just created an internal alkyne, what 2 products can I get when I run oxymercuration on my alkyne? Why don't you work in your groups for the next 5 minutes and try to predict the final products of this synthesis? What are the 2 organic structures that form as a result of the oxymercuration? No, that's a good question. You guys are asking where did the bromines go and the chlorine? They got substituted. I substituted a bond from carbon to bromine for a bond from carbon to carbon. The bromine was substituted. If you wanted to show byproducts, this gives a byproduct of H2, and then this gives a byproduct of NaBr, and then this gives another byproduct of H2, and this gives another byproduct of NaCl. The halogens are leaving. We call them leaving groups. And the alkynes are coming in, substituting the halogens. Great question. What do you know about oxymercuration? We know that it forms a certain type of functional group, right? And it likes to do that with regiospecificity. It forms a ketone on the more substituted carbon. Which carbon here is more substituted? 1 or 1 prime? They're equally substituted. 1 and 1 prime are both bonded to other carbons. So they both could be the more substituted carbon, which means they both could form the ketone. That's why we get two products. That's right. So map your carbons again so that you can show one forming on one forming on one. Catch that? Was this one? Wait. Right. You're one carbon short and the whole benzene ring short. Yes. No, you got it. That is the right number of carbons. Oh, this one then too. This one needs the benzene. From my summer lectures. Good.
No.
Good. I see. Good work. We know what functional group this reaction is, right? What functional group should I get out of this? Right. Which means I added carbonyl CO double bond to the more substituted carbon. Which of these is more substituted? Right. So which one gets the ketone? Oh, that's why. Well, it's actually going to be a CO double bond now. So let's pay attention to how it goes here. It went from linear to being just a normal fixation.
I
Even
know
here,
almost
linear
like I'm
to normal
so
fixation. You're going to go back to normal
page
fixation.
notes like
Yep.
lost. Like,
We're on the
we're
right.
actually
Good. Great. Oh,
Yeah, so that's the same.
good work. Nailed it. Way to go.
Oh, like an additional. Okay. I see what you're saying.
Yep. What two things would you get? There you go. Yep. You have just completed your first multi-step synthesis reaction. And this is pretty much where we go for the rest of the semester. We're going to keep adding in reactions, but we're going to see how these reactions can start playing one after another. Alkylation, followed by alkylation, followed by oxymercuration. We could have done alkylation, partial hydrogenation, and then HX addition. All different reactions, all steps that we've known. So we're just making a multi-step synthesis. Our two products here, we're forming the ketones on positions 1 and 1 prime. Here was position 1, 2, 3, 1 prime, 2 prime, 3 prime, 1, 2, 3, 1 prime, 2 prime, 3 prime. And somebody tell me, why did I form a ketone on both carbons? Equally substituted. Oxymercuration is a regio-specific reaction if there's a regio difference. Here there is no regio difference, so I get structural isomerization in my products. Let me ask you this. Could I have used hydroboration oxidation on this reaction? Yes. Would I have formed an aldehyde? No. There's no potential of forming an aldehyde here. Hydroboration oxidation is also regio-specific when it's possible. And in this case, hydroboration oxidation would have given the exact same products. So how would you decide which one to use? I don't know, do you like to work with mercury or do you like to work with boron? What chemicals do you have in your lab? What is going to dissolve in your solvent best? What is going to avoid reactivity with the rest of your molecule? Those are all thoughts that go into deciding the reagents. All right, guys, I'm sorry I've taken you a minute over. Good work. On Monday, we have Monday lecture, but not Wednesday next week. On Monday, we'll start off with some thought problems about multi-step synthesis, and then we're going to look at a few other reactions as we look at section 10. Have a good weekend. I will see you on Monday.